We are back with extrinsic regulation of blood flow. And man, this old rock and roll gets my heart pumping, man. It gets my blood flow moving. It gets my stroke volume up, my heart rate going. This is All Along the Watchtower by Jimi Hendrix. Anyways, let's get on with the video. So we're talking about extrinsic regulation due to the release of norepinephrine by the sympathetic division of the autonomic nervous system, or activation of the adrenal medulla, which results in the release of a mixture of epinephrine and norepinephrine into the bloodstream. Remember, bloodstream, it's going to come into contact with its receptors throughout that circulatory system. As a review, both sympathetic and parasympathetic divisions of the autonomic nervous system have preganglionic neurons that release acetylcholine that bind to nicotinic receptors on cell bodies of postganglionic neurons. Where the difference is, there they are, postganglionic 1, postganglionic 2. The difference is found in the neurotransmitters that are released by postganglionic neurons of these two divisions. The sympathetic postganglionic neurons release norepinephrine. The parasympathetic postganglionic neurons release acetylcholine. They're going to bind to their respective receptors on the target tissues. Adrenergic receptors for the sympathetic division, muscarinic receptors for the parasympathetic division. You absolutely must have these systems down cold. I told you they are like Jack Bauer from the Series 24. He's a government agent. He's trying to prevent terrorist attacks. And if he thinks you have information that he thinks that you know, he's going to ask you nicely the first time. And if you think by simply telling him, "Hey Jack," that's Jack, by the way, "I don't know. Leave me alone. I don't know your answer. Go away." Like this autonomic nervous system, he's going to keep asking you questions. He's going to keep asking you questions over and over again, just like me. You're going to need to know this system. All right, there we go. Let's focus on norepinephrine. Okay, has effects on various tissues that result from the interaction between norepinephrine and the specific receptors found on that tissue. Epinephrine is also going to exert its effects through specific interactions with receptors found on its effector tissues. So here in this chart, left-hand column, I have receptor types, alpha 1, beta 1, beta 2. I have their respective affinities for norepinephrine and epinephrine. Also have the effector tissues that express those receptor types. We're going to see what the effect of the interaction between norepinephrine and epinephrine with their receptors, what effect that will have on these effector tissues, and then what's going to be the net result, the consequent result of that interaction. So, both norepinephrine and epinephrine can bind to alpha-1 receptors and exert effects. They're going to exert the same effect, which is contraction of smooth muscle in arterioles that express alpha-1 receptors. Where are they expressed? Throughout the body, as well as in veins. So this interaction between norepinephrine or epinephrine with alpha-1 receptors is going to result in vasoconstriction and venoconstriction. All right. What about in cardiac tissue? Well, beta 1 receptors on the heart itself. So not on the arterioles, but on the heart tissue itself. That's where beta-1 receptors are expressed. Either norepinephrine or epinephrine can bind to beta-1 receptors, which results in increase in heart rate as well as increase in the force of ventricular contraction. We're going to focus more about this in the next lecture. So I'm not going to focus on it too much this lecture. Okay, I'm just bringing it up now. We're going to recall it in our next lecture. Finally, we're going to talk about beta-2 receptors. Okay, they are only responsive to epinephrine, and they are selectively expressed in smooth muscle and arterioles, bringing blood to the cardiac contractile cells, heart muscle, skeletal muscle cells, as well as the skin. And they're also expressed in smooth muscle in the bronchioles. Now, only epinephrine can bind to beta-2 receptors, and its result is relaxation of smooth muscle. So epi plus beta-2 equals relaxation of smooth muscle, which means we have selective vasodilation, selective dilation of arterioles, bringing blood to cardiac cells, skeletal muscle cells, as well as the skin. And cardiac cells, I mean contractile cells. All right. Now, I did mention venoconstriction, but for the purposes of this section of the lecture, we're only going to focus on vasoconstriction or vasodilation, and that means we're going to be talking about increasing or decreasing the diameter of arterioles. Quick review: vasoconstriction, decrease in arteriolar diameter. Vasodilation, increase in arteriolar diameter. If I decrease the arteriolar diameter, I increase the resistance to flow into the arterioles, I increase total peripheral resistance, and I reduce blood flow to those tissues served by those arterioles. Vasodilation, I increase arteriolar diameter, which means I reduce resistance to flow of blood into those arterioles. I reduce total peripheral resistance there, and I increase blood flow to the tissues served by those arterioles. All right, let's talk about increased sympathetic tone. We're going to focus only on norepinephrine release at this point by autonomic postganglionic neurons of the sympathetic division. I activate those alpha-1 adrenergic receptors in the arteriolar smooth muscle. Remember, those are expressed globally. I'm going to get vasoconstriction of arterioles everywhere throughout the body, which is going to then result in a reduction in blood flow to all tissues throughout the body, with norepinephrine only. All right? Cool. What about epinephrine? What about activation of the adrenal medulla? Epinephrine binds to both alpha-1 and beta-2, has a greater affinity to beta-2. So we're going to see how these two factors come together to affect blood flow. So beta-2 receptors are selectively expressed on arteriolar smooth muscle and cardiac muscle, skeletal muscle, and skin, as well as smooth muscle in bronchioles. So if I activate the adrenal medulla, there's the potential to activate both alpha-1 and beta-2 receptors in arterioles that are bringing blood to cardiac muscle, skeletal muscle, and skin. This is going to result in vasodilation of those arterioles due to a couple of factors. Number one, epinephrine preferentially binds to beta-2 over alpha-1. What does that mean? That means if I had an arteriole bringing blood to skeletal muscle, and I filled that smooth muscle, if I expose those smooth muscle and those arterioles to epinephrine only, most of that epinephrine is going to bind to beta 2 receptors, which is going to result in relaxation of that smooth muscle in those arterioles. So the degree of relaxation exerted by the binding of epinephrine to beta 2 is going to outweigh the constriction that would result from the binding of epinephrine to alpha 1. You got me? Cool. Second, there are more beta 2 receptors than there are alpha 1 receptors in these arterioles, the arterioles bringing blood to cardiac muscle, skeletal muscle, and the skin. So combining these two factors, when you get the release of epinephrine and norepinephrine from the adrenal medulla, the net result is vasodilation in these arterioles, which is going to increase blood flow to cardiac muscle, skeletal muscle, and skin. What about in other arterial or smooth muscle? Well, you only find alpha 1 receptors in the arteriolar smooth muscle bringing blood to these other tissues, such as the GI tract, the kidneys, and the bone. So, you're going to have similar levels of vasoconstriction if you released epinephrine and norepinephrine in these arterioles. So you'll get a similar effect as we see with the increased sympathetic activity, which results in the release of norepinephrine in smooth muscle in arterioles bringing blood to the kidneys and the GI tract, with the result that you get further reduction in blood flow to these tissues. So, during stress, exercise, or significant drop in mean arterial pressure, we're going to get activation of the sympathetic nervous system that leads to activation of the adrenal medulla. This is going to do a couple things. Number one, increase the release of norepinephrine by sympathetic postganglionic neurons throughout the body, and the release of epinephrine and norepinephrine from the adrenal medulla into the bloodstream. What's the net effect? Similar to what's observed with the activation of adrenal medulla alone. We're going to get what we call global vasoconstriction throughout the rest of the body, those arterioles bringing blood to kidneys, GI tract, bone, some other areas, as well as selective vasodilation in arterioles bringing blood to cardiac muscle, skeletal muscle, and skin. Okay, what about hormonal control? Well, there's three here. The first one, epinephrine released by the adrenal medulla, we already talked about. So I want to focus on these other two hormones, vasopressin and angiotensin II. Vasopressin, also known as antidiuretic hormone, you may abbreviate it as ADH. It is involved with the maintenance of water balance. So if you get increased release of ADH, that's going to promote water retention during urine formation, which results in an increase in blood volume. Angiotensin II is part of what's called the renin-angiotensin-aldosterone system, the RAAS, and this is an important system that regulates sodium balance. If you activate the RAAS, this is going to promote sodium conservation, again during urine formation, leading to water retention and increased blood volume. We're going to be talking more about these two effects more when we get to the renal system. The main point I want you to take away from for this section is that both ADH and angiotensin II are potent vasoconstrictors, which means that their release of either one of these leads to a global increase in total peripheral resistance and a reduction in flow to tissues throughout the system. Thank you. And with that, this video is complete.